Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to Lesson 4. This is modeling a context from a graph. Okay, so the first thing I'm going to do is read example 1, and it says read the problem below. Your teacher will walk you through the process of using the steps in the modeling cycle to guide your solution. So if I come over here, this is the modeling cycle. So let's just talk about this for a second. So we are presented a problem. Example 1 is a problem. Okay. We first try to formulate an equation of a model. And then we compute it, and we check some points, and then we interpret our data. And then after interpreting our data, we validate. Either it's going to be valid or invalid. If it's valid, you report and say, okay, this is what it is, and we're done. If it's not valid, then you need to repeat the process. So then you would go back to formulate and start over and work around again. And so we're going to formulate, compute, interpret, validate, and it's going to be a circle around. You may not get it the first or second time, but eventually you will get it, and then when you do, you report your findings. So that is the process of the modeling cycle. Okay, so the first thing we want to do is determine our units of measurement that are involved in the problem. So I look at my x-axis label and my y-axis label. The x-axis is labeled leg length in feet, and the walking speed of an animal is feet per second. Okay, so leg length is in feet. So length of one of the legs in feet, and its walking speed in feet per second. Okay, so if we use x to represent the number of feet, and let me write that in. Okay, so I put this. Let x equal number of feet in leg length. And we'll let f equal speed based on leg length. So since we're doing that, I'm going to label this over here my x-axis, and this up here is going to be my f-axis. Okay, the next thing we want to do is try to determine what type of function we're dealing with. Okay, so if it was straight like this, whoops. Okay, try that again. So if we had a straight line, obviously it'd be linear. Okay, this has a curve, so it's not linear. If it looked like this, right, or this, it would be a parabola. This does not look like a parabola. It looks like a sideways parabola. So this could be a square root function. Remember, square root function is the inverse of a parabola, which is a reflection across y equals x. But we usually only look at half of it. Otherwise, it wouldn't be a function. So this could be a square root function, but it also could be doing this. Okay, and that could be a cubic function and only looking at the right side. So we've narrowed it down to either a cubic, positive, anything greater than 0, or a square root function that's 0 to the positive infinity. Okay, so the first thing we're going to do is try to see if this is a square root function. So I'm going to write 3 functions here. I'm going to call one f of x, and that's just simply going to be the square root of x. And then I'm going to write g of x. And I'm going to call that the square root of some constant a, or a coefficient a times x. So we can have a scale multiple that makes it grow faster. And then finally we can have a shift. And that could equal the square root of x minus some letter b, which would shift it to the right or left. And then we want to test each of these. So the first thing I want to do is test f of x. And since we're given 2 points, we have a point 2 comma 8. Keep in mind that's x comma y. Then I plug that into f of x, so I'd say f of x, well x is 2, so f of 2 has to equal 8. Okay? So given that 2 comma 8 position, that's going to yield, let me write it this way. If I take this 2 comma 8 point, okay, that is going to yield an 8. That's saying that y equals, because that's what f of x is, y equals the square root of x. Well, obviously 8 is not the square root of 2. The square root of 2 is 1 point something. So it is definitely not f of x. Then I'm going to go on to g of x. And I'm going to use the point 2 comma 8. So I'll use blue this time. So I'm going to use the point 2 comma 8 again. And that is going to give me 8 for my y. So that's saying y, or g of x, equals sum a times 2, or 2a. Okay, a times x, x is 2, a2, we don't write a2, we write 2a. Okay. Okay, so now I know that what underneath the radical, what square root, the square root of what number is 8. I know that is 64. So I'm going to now say that that's got to be 64. Why did I write 16? I don't know. It's got to be 64. So now I'm saying the square root of 2a equals 64. Or 64 equals 2a. And then when I divide both sides by 2, I get 32. Okay? And then I do the same with 8/16. So I have this point here, 8 comma 16, 8 comma 16, and we want to yield that y to be 16, or 16 equals the square root of 8a, because now x is 8, so that's now going to be 8a. Okay, and 16 squared is 256, so now I know that 256 equals 8a. Okay, and then when I divide both sides by 8, I find a, and I get a to equal 8 times 3 is 24, remainder 1, 8 goes into 16 2 times, so a is 32. So that gave me the same a. So it looks like this is in the form of g of x equals 32x. So now I know my a. So the function now I believe to be g of x equals the square root of 32x. So if I plug in 0, 0 times 32 is 0. The square root of 0 is 0. That would be this point right here. Plug in 2, 32 times 2 is 64. The square root of 64 is 8. That's this point here. Plug in 8. 8 times 32 is 256. The square root of 256 is 8. I'm sorry, the square root of 256 is 16. That's my y. So these values are all checking. So g of x equals the square root of 32x. Now it says a T-Rex leg length was 20 feet. What was the T-Rex's speed in feet per second? So g of x is square root of 32x feet per second. We don't want to forget our unit of measurement. So this is going to be feet per second. So now I want to know when x is 20. So now I want to calculate g of 20. So g of 20 equals the square root of 32 times 20 feet per second. Okay, so g of 20 equals the square root of 640 feet per second. Now when I get my calculator out, I want to see what the square root of 640 is. And it's 25.29812. And so let's just round that. So now I would say g of 20 is approximately 25.3 feet. Okay, now when I go back up to this graph, now watch what's going to happen. If I draw a line segment and I line it up at 20 and I bring it to here, and then I bring that 20 over to here. Oops. Let's try that again. Try to make it right there. And let me just fix that a little bit. Okay, so what I'm saying is you go up to the function at 20 and you go over, and that is 27 up here, 18 down here. 25.3 is closer to 27 than 18, so this does look like that is the correct answer. And that's one way you can check your solution. Okay, page 2, exercises. Now practice using the modeling cycle with these problems. Eduardo has a summer job that pays him a certain rate for the first 40 hours per week and time and a half for any overtime. The graph below is a representation of how much money he earns as a function of the hours he works in 1 week. Eduardo's employers want to make him a salaried employee, which means he does not get overtime. If they want to pay him $480 per week but have him commit to 50 hours a week, should he agree to the salary change? Justify your answer mathematically. So A says formulate. Recall this step from lesson 1. So 1, formulate. The first thing you do is what type of function can be represented by a graph like this? Example, quadratic, linear, exponential, piecewise, square root, or cubic, or cube root. Okay, so this looks like a straight line right here up until this point right here. Okay, so right up until this point right here, that is a straight line, but then it changes slope, and this is a straight line from here to here. Okay, so if it's straight, it can't be quadratic, it can't be exponential, it can be piecewise, it can be linear, but a line never kinks in the middle, so it's not quadratic, it's not exponential, it's not linear, it is not a square root function, and it's not a cube root function. So therefore it must be a piecewise function. Okay, we have two pieces that are both linear. Okay, so the graph is a function that is piecewise defined and made up of two linear functions. Okay, so there it is. Piecewise defined, made up of two linear. Okay, continuing on, part 2. How would you describe the end behavior of the graph in the context of this problem? Okay, so there are limitations to work, obviously. So if we're talking about time in hours, there's only so many hours per week, so this does not go to infinity. There are 24 hours in a day, and 24 times 7 is 24 times 7 days a week. There are only 168 hours in a week, so I can't go to infinity. The most you could work is 168 hours a week, but nobody's going to be able to work 7 days a week, 24 hours a day. So there is a restriction to the maximum, and you can't work less than 0 hours. So we're going to start at 0, 0, so we're only in the first quadrant. And these are all the things you need to think of when you're doing a problem. Okay, so I'd word it something like this. As x gets infinitely large, so does the function. However, realistically, there is a limit to how many hours per week he can work. So there is a maximum value for this function. Okay. Okay, on to page 3, part 3 of problem A. How does this affect the equation of our function? So I'm going to be going back and forth now. Okay, so how does this affect the equation of our function? It's piecewise. And the equation of our function, we know this slope is positive, we know that slope is positive, so all the slopes are positive, but we're not going to go less than 0 hours. There's no such thing as negative hours, and so therefore I'm going to restrict the domain. And as we said before, there's a maximum number of hours we can work in a week, so there's a restriction on the range as well. Okay, so that's the answer to this question right here. So we'd say the slope of each graph is positive. We may need to state restrictions on the domain and also on the range. Part B says, I, or 1, what strategy do you plan to use to come up with the model for this context? Okay, so what strategy do we plan to use to come up with the model? Well, again, we need to find the slope, and we need to determine what our restrictions are. So we need to identify the domains for each piece, linear function, in the piecewise function. We need to find the slope and the y-intercept for each linear piece, and then put the equations in slope-intercept form. Okay, so there we go. That's what we need to do. So part 2 says, find the function of this graph, show all of your work. Okay, let's start by restricting our domain. So if I go back to this function, our domain is the x-axis. So we're starting at 0, and this ended right here at 40 hours. So that's a full-time work week. So we're going to restrict our domain from 0 to 40. Okay, so this is what it would look like. For the lower piece, the domain is all x values between 0 and 40 inclusive. Okay, that's why we have less than or equal. Okay, so there's our restriction on our domain. And then if we go back, what is the y-intercept of this? Well, the y-intercept is right here. It's 0. So we can state that. So let's do that. Let's see. So y-intercept equals 0. And then we have points that we were given. So let's go back and look at those. So we have the point 0, 0 and the point 22, 196. So we're going to use those, or 198, I guess that is. Okay, so we're going to use the point 0, 0, and the point 22, comma, 198. Those are our two givens. Now remember, when we want to find the slope, so our equation is y equals mx plus b. And we know our y-intercept is 0, so it's just going to be y equals mx plus 0. Okay, or just mx. Now I need to find the slope. Remember, slope, m, equals y2 minus y1 over x2 minus x1, which equals 198 over 22. And that reduces. Half of 19 is 9, so 99 over 11, and that comes out to be 9. So our slope is 9. So our equation is y equals 9x. Okay, so I just changed the color on this, so this is our first piece, and then I can erase all of this. And now we need to do the same for the second piece. All right, so now we're working on the upper piece, and we need to look at the domain restriction. So on the upper piece, we're going from 40 to 72, 76, that's 80. So we're going from 40 to 80. But that's all it's showing on the graph. We could work more than 80 hours a week. I wouldn't want to, but you could. So our domain is going to be greater than 40. So we want to deal with 40 and up in this case. So I will write that. Okay, so here we have it. For the upper piece, domain is 40 less than x. In other words, our x is greater than 40. So we could write x is greater than 40, or 40 is less than x. Okay, so what next? Well, we need to determine some values. So let me switch to a different color here for this part. Now, keep in mind that this 9 right here is dollars per hour. So if he works 1 hour, he makes $9, 2 hours, $18, 3 hours, 27, and so on. So 9 is our rate, our pay. So for this part of the problem, we have to use the context of the problem and the graph. So up to this point, Eduardo has worked 40 hours, right? So up to this point, he's worked 40 hours, and he has earned $9 an hour. So if you think of that as 40 hours times $9 an hour, then that is $360. Okay, this is the y value when x is 40. So now I know that when x equals 40, y is 360. Okay, because it's $9 per hour. All right, so for the second linear equation, we again find the slope. So setting the 2 points, we have, we're given, I think we're given another point here. Yeah, 70 right here. That is 70, comma, 765. So we have the point 70, comma, 765 as well as 40, comma, 360. Okay. And we also have another point over here, and that was 60, comma, 630. So we're going to use all these values. Like one too many. So we're also going to use 60, comma, 630. So when you work 60 hours, you make 630, 70 hours, you make $765. That's what that means. So we want to select the 2 points on that line, not using this endpoint, and so we would use these two to find our slope. So remember, our m equals y2 minus y1, 765 minus 630, divided by 70 minus 60, which I'll just do right here as 10. 765 minus 630 is 135, so if I divide that by 10, I get my slope to be 13.5 or 13.5. Okay. So looking at the graph, we also see that the second line was moved 40 units to the right, so it's translated 40 units. So what they're saying is this linear equation, if it was over here at the y-axis, this point would be right here. Well, we shifted it to the right 40 units to put it there. So what does that do to our y-intercept is what they're saying here. So we can manipulate this and we can say something like so. We can call the function f of x, and that equals, we know the slope now is 13.5, and we had shifted x 40 units to the right, so that's minus 40. Remember, it's opposite when it's inside parentheses. And then plus our value at that 40, which was 360. That's our y value, 360. Sorry for cramping this up. Let me move this a little. Okay. And that is 360. So let me rewrite that so it's not crammed. Okay, so there's our equation. F of x equals 13.5 times the quantity x minus 40 plus 360. All right, that's if x is greater than 40. If f of x is less than 40, well, what was going on here is we're going to have we're going to have two equations. Okay, so we have 13.5 times x minus 40 plus 360, but we also have this function over here, which is 9x. So the function is either this or this, depending on. So when this one here is less than 40, and this one over here is if 0 less than or equal to x less than or equal to 40. Let me just move all this stuff out of the way here. Okay, so this is 360 if x is greater than 40. Okay, so there's our equation. Okay, so part C says to interpret. How much does Eduardo make an hour? Well, if it's 40 hours or less, he makes $9 an hour. And if it's more than 40 hours, it's $13.50 an hour. Okay, so there it is. Part 2. By looking only at the graphs, which interval has the greater average rate of change? X less than 20 or X greater than 45? Justify your answer by making connections to the graph and its verbal description. Okay, so we need to go back and look at the graph when X is less than 20 and X is greater than 45. So here's 20. So looking at the graph here, here's the slope they're talking about. And then looking at 45, which is here roughly, we're looking at this graph up here. Well, obviously this is steeper than this. So what we would say about that at this point is the verbal description states that Eduardo gets paid more after 40 hours of work. Because if you look at how steep the graph is after 45 hours, you can see that it is increasing at a faster rate than when it was 20 hours or less. Okay, the slope was steeper. Okay, page 4. Eduardo's employers want to make Eduardo a salaried employee, which means he does not get overtime. If they want to pay him $480 a week, but have him commit to 50 hours a week, should he agree to the salary change? Justify your answer mathematically. Okay. So we want to pick a value that is greater than 40 and then check. So let's just say he works 50 hours. 50 hours a week is right here. Okay, he wants to, and so we want to see if this would justify. So we want to take our f of 50. We want to find f of 50. Okay, and that equals our equation that's greater than 40. So I come back here, anything greater than 40, we would use 13.5 times x minus 40 plus 360. So that's going to equal 13.5. That's our slope, or our rate of change, or his pay rate, times, now it was x minus 40, but our x is 50 now. So you write 50 minus 40, okay, plus 360. Okay, so what will that give us? Well, that's going to equal 13.5. Let me just clean that up. Put the decimal in the wrong place. 13.5. And now 50 times minus 40 is 10. So times 10 plus 360. And 13.5 times 10 is 135. 135 plus 360, and 5 plus 0 is 5, 3 plus 6 is 9, and 3 plus 1 is 4. So f of 50, or what he makes for working 50 hours, is $495. So he'd get paid more as an hourly employee if he worked 50 hours a week, because 495 is more than 480. Okay, so it says to justify your answer mathematically, you get an answer, but you still should say, you should come up with a summary. Okay, so I just plopped this over my work. He would get paid more as an hourly employee if he worked 50 hours a week. It seems that it would be in his best interest to keep the hourly agreement rather than the salary. Students may come up with other responses, but should at least understand that Eduardo earned more money for 50 hours of work as an hourly employee than he did as a salaried employee. Okay, so if you show that understanding, then you have answered the question correctly. Okay, now it says, how can you check to make sure your function models the graph accurately? Okay, and the answer to that is right here. For the values in our graph, we can substitute the x values into the function to see if the same given y value is a result. So in other words, I could go up to 50 and see if 495 is correct. I could go back to my graph and draw a segment, and I'm going to change the color. How about red, thin? From 50 is halfway between 48 and 52, so this would be going up to our graph there, and then another segment bringing it over here, and that would give us our approximate value, how much he made for 50 hours, which is between $481 and $550. Okay, and we got 495, which is between 481 and 550. All right, part two, or number two, question two. The cross-section view of a deep river gorge is modeled by the graph shown below, where both height and distance are measured in miles. How long is a bridge that spans the gorge from the point labeled 10? Okay, so that's a bridge going from here, 10, to the other side. How high above the bottom of the gorge is the bridge? Okay, so I drew a couple of line segments in here for your visual. The green horizontal line from the point 1, 0 over to the other side would be our bridge span. And the red vertical segment is at the bottom of the gorge, which would be our vertex of our parabola, up to the bridge. Okay, so there's a visual. So the question's asking two questions. How long is the green segment, and how long is the red segment? Okay, so it says, what type of function can be represented by the graph like this? Okay, so looking at this, obviously it is not linear. So I'm going to cross linear out. It is not exponential. Exponential would look like this, going up forever, or down exponential would go like that. Okay, so it's not exponential. Piecewise, well, it could be piecewise if these are different on either side. It's not a square root function because square root functions would be rotated 90 degrees, so it's not a square root function. And a cube root function. Would it be a cube root function? I don't think so. So if you want to review some of these, it's sometimes a good idea to just put something in the calculator, go to y equals, and what would a cube root function look like? Well, you go to math, 4 for cube root of x, and graph it, zoom 6. Okay, so here's what a cube root function looks like. So this does not appear to be a cube root function as well. So it looks like a quadratic, but it could be a piecewise. We don't know if they're the same or different on either side of any point. But I would assume that this is definitely a quadratic. Okay. Okay, on to page 4. Part 2 of this question says, what are the quantities in this problem? So if I go back and look at the graph, well, the quantities would be the distance in miles of the bridge and the height in miles of the bridge from the bottom of the gorge. So put that into words, and it would say the quantities are the height relative to the location of the bridge, f, and horizontal distance from the highest point in the gorge, x. Part 3. How would you describe the end behavior of the graph? Okay, so the end behavior of the graph is basically saying it's going up. As we go to the left, the gorge is getting higher. As we go to the right, it's getting higher. So this is opening up. So you could just say that, opening up. Okay, number 4 says, what is the general form of the function type? Okay, so if we're going to say that this is a parabola, which we are, then what all they're saying is, what's the form of the function? So you could say f of x equals standard form, which is ax squared plus bx plus c. Okay, if you wanted to do vertex form, then you would say f of x equals a times the quantity x minus h squared plus some constant, or k. Okay, so there's standard form and there's vertex form. Okay, v, well, there is one other form. F of x equals a times x minus m times x minus n. Okay, and in this function here, m and n are your x-intercepts. So if I went back to this graph, oops, went too far. Okay, go back to this graph. The x-intercept was 1, 0, and looks like 2.5, 0, but it could be a little less. Okay, so if we knew the x-intercepts, we could use this equation, but I would not use that in this situation. Okay, part V. How do you know the function type and end behavior affect the equation of the function for this graph? How does knowing the function affect? Okay, the equation is a second-degree polynomial, quadratic, where the leading coefficient is positive. Leading coefficient is positive because it's opening upward. So A is positive in this equation here. Part 6, what is the equation we would use to model this graph? Okay, so we're going to use the 3 ordered pairs in the graph. So let me choose red. And we were given the point 0, 5. Okay. So we have the point 0, 5. We're given the point 1, 0, and we're given the point 3, 2. So instead of going back and forth, I'm just going to write these down right now. We're given the point 1, 0, and we're given the point 3, 2. Those are the 3 points we are given. All right, so going back to here, using the point 0, 5, and we use this equation here. So it's going to be f of 0 equals a x squared. Actually, why waste time here? If that's the point 0, 5, we know the y-intercept. That's the y-intercept, and that is our c. So we know that that is c equals 5, and therefore that gives us f of x equals ax squared plus bx plus 5. Okay, now substitute the other 2 ordered pairs to form a linear system. So now if I use the point 1, 0, I'll switch to green for this now. So now we're going to use the point 1, 0. Now x is 1. So that would be a 1 squared plus b 1 plus r5. And that equals 0. Because that is our y, f of x is y, so that equals 0. So therefore we get 1 squared is 1 times a, so that will simplify to a plus b. Move the 5 over to the other side. A plus b equals -5. Okay. Okay, so now we're going to do the 3, 2 portion. So let me choose blue. So now we're doing x is 3, y is 2. And we're going to substitute it in here. So then it's going to be a x is 3 squared plus b times 3 equals -5. Actually, let me do plus 5 first, like I did before. Plus 5 equals 2. Okay, I was getting ahead of myself there because I don't have the y of 0 in this case, which I did here. So I forgot to do this 2. So if you follow this, here's my x, and my y, or f of x, is 2 in this case right here, 2. Now simplify, so I get 3 squared 2a plus 3b equals, now subtract 5 over the other side. 2 minus 5 is negative 3. Okay, so now we're going to finish this by solving a linear system. So I have a plus b equals negative 5. I have 9a plus 3b equals negative 3. So if I take this a plus b and multiply it by negative 3, then that is going to yield negative 3a minus 3b equals positive 15. And then when I line up this 9a plus 3b equals negative 3, then I can solve this. Negative 3a plus 9a is 6a. Negative 3b plus 3b is cancels. 15 plus a negative 3 is 12. Divide both sides by 6, and a is 2. So if a is 2, substitute it in. 2 plus my b equals negative 5. And subtract 2 from both sides, b equals negative 7. Okay, so now I have a equals 2, b equals negative 7. So the equation is right here, ax squared plus bx plus c. My answer is now f of x equals ax squared plus negative 7, so I'm just going to say minus 7x plus 5, which we got from this equation here. So a is 2, b is negative 7, and the c was 5. Okay, on to page 6, part B says to compute. What are the key features of the graph that can be used to determine this equation that we just found? Well, if we look up here, we were given the y-intercept. We were given the one of the x-intercepts and then another point. So that's what we would say. The y-intercept and the other two given ordered pairs. One just happened to be an x-intercept. Part 2 says which key features of the function must be determined. Well, in order for us to find the distance from here to here, we need to know the other x-intercept and we need to know the vertex. So that is the other two things we need. Okay, so the zeros and the vertex must be determined. We have one zero, we need the other, and we need to know the vertex was at the bottom of this red segment. Part 3 says calculate the missing key features and check for accuracy with your graph. So the function we've come up with is f of x equals, and this is from the previous page, 2x squared minus 7x plus 5. Okay, so I want to factor that. And I'm just going to do it real quickly over here. I have a different way of doing it. I multiply my a times my c and change it to a 1 in front. And 2 times 5 is 10. And then I factor that. It just makes it easier. This is how I do factoring when leading coefficients, not 1. So factors of 10 that add up to 7 are 5 and 2. 5 times 2 is 10. 5 plus 2 is 7. They both need to be negative because a negative times a negative is positive. Negative plus a negative is negative. But I multiplied by 2, so now I need to divide by 2. And when you divide by 2 and you get an integer, you're all done. But if you don't, then that's your leading coefficient, 2x minus 5. So there it is factored. So we have f of x equals, and then I'll just bring this over, 2x minus 5 times x minus 2. Okay, so there's factored form. So x equals 2 is one of the x-intercepts, and the other one is 2.5. Oh, I'm sorry, it's not x minus 2, is it? That's what I was getting confused about here. 2 divided by 2 is not 2. 2 divided by 2 is 1. My fault. And that's why I was questioning it, because I already had this one, because this would mean that x equals 1 and x equals 5 halves, or 2.5. Okay, and so that's this point right here. That would be the point 2.5 comma 0. Alright, 2.5 comma 0 and 1 comma 0 are our two zeros. So the distance would be 2.5 minus 1, which is 1.5 miles. Okay, so that's the distance from here to here, 1.5 miles. Okay, and to find the vertex, let me change colors. To find the vertex, it is the midpoint between the two zeros. So if I have one zero at 1 and the other 0 at 2.5, then it would be 2.5 plus 1, or 3.5 divided by 2. Midpoint is add up the ends and divide by 2. Then that would be 1.75. So that's my x value, 1.75 comma something. So I plug that into my equation, and just to save time, I'll calculate it off to the side here. I'll do it in my calculator. That'd be 2 times 1.75 squared minus 7 times 1.75 plus 5, and that would give me a negative 1.125, negative 1 1/8. Okay, and that's that distance there. So since that is a height of 0, and this is down 1.125 miles, then now I know that the distance, the height of the bridge, is 1.125 miles. Okay, it says, what domain makes sense for this context? Explain. So your domain is your x's, okay? And we have one domain here. This goes to 0, comma 5. So this is 5 miles above the ground, above 0. And this one is cut off, so we don't know. So since x is the horizontal distance from 0 to 5, the domain makes sense. The domain that makes sense, x is the horizontal distance from 0 to 1, 2, 3, over to 5. Or I should say 0, comma 5, my fault. Since x is a horizontal distance from this point to the other side of the gorge, which is cut off, then it makes sense to have a domain x is greater than 0. Okay, what domain makes sense for this context? X is greater than 0. Okay. In order to know the upper limit of the domain, we would need to know the height of the highest point on the other side of the gorge, which can't be determined because it's cut off here, but we'd assume it to be 3, here is 4 miles, so I'd say a little between 4 and 5 miles. Okay, probably close to 4.5 miles, but that's just an approximation. Now part 2 says, how wide is the bridge with one side located at 1, 0? Okay, it's the difference between the x coordinates, which I've already explained. So it's right here. So all I will do is move this down to here. So 2.5 is this point here, minus 1 is 1.5 miles. Then it says, how high is the bridge above the bottom of the gorge? The minimum value of the function represents the lowest point. Since the height shown on the graph is relative to the location of the bridge, this bridge would be 1.125 miles above the bottom of the gorge. It's the y-coordinate of the minimum point, or our vertex. Okay, so it's the y value right here. So it's 1.125 miles. Don't put a negative here. That just means below. The ground is 1.125 miles below the bridge. Okay, page 7. Part 4 says, suppose the gorge is exactly 3.5 miles wide from its two highest points. Okay, so let me just draw that. So let me use a segment, and let's see, what have I not used? Red. Make it kind of thin. And so what they're saying is right here over to here. That's what we're trying to find. So it says, suppose the gorge is exactly 3.5 miles wide from its two highest points. All right, so 3.5 miles, that would mean I would move this down to right here. So 3.5 miles is right there. Find the average rate of change for the interval from x equals 0 to x equals 3.5. In other words, 0 to 3.5. Explain this phenomenon. Are there other intervals that will behave similarly? Okay. The average rate of change for that interval is 0. The 2 points are points of symmetry straight across the curve from each other. The line passing through them is horizontal. Any interval with endpoints that are symmetry points will be horizontal as well with a slope of 0. Now part D says to validate. And that says, how can you check to make sure that your function models the graph accurately? Okay, well, then all you'd have to do is substitute values in and see if they match the graph. So how would I say that? Right here. We can substitute any x values from the graph into the function to see if the resulting y value is reasonable for the graph. So if I plugged in 2 and got -1, that would be reasonable. If I plugged in 3 and got 2, it would obviously be reasonable. Okay, number 3. Now compare 4 representations that may be involved in the modeling process. How is each useful for each phase of the modeling cycle? And explain the advantages and disadvantages of each. Okay. One representation is the verbal description. The verbal description helps us define the quantities and, in this case, write the factored form of the equation for the function. We always need to find another representation to analyze or interpret the situation. Okay, the graph is visual and allows us to see the overall shape and end behavior of the function. We can see some integer values of the function, but must estimate any non-integer values. The graph is a good way to check calculations to make sure results are reasonable. The table in general does not help us see shapes, patterns in x minus y any better than the graph does. However, a table with equal x intervals does help us see the patterns in y values very well. So we could, and what they're saying is you could go into your calculator, plug in the function, and then go to table. Go to your table and look at values. That's what they're talking about here. Okay, and finally, the equation allows us to accurately calculate values of the function for any real number. It can be written in various forms to help us see features of the function: vertex form, standard form, factored form. It allows deep analysis and is sometimes referred to as an analytical model. Okay, on to page 8. That is the end of lesson 4. Review the lesson summary and go to your problem set.